Hi guys, in this particular video we'll be discussing the problem of the day for Geeks for 3rd of January. The problem's name is minimize number of students to be removed. It's a very interesting problem, and the problem states that n students of different heights are standing in attending an assembly. The heights of students are represented by an array h. The problem is that if a student has less or equal height than the student standing in front of him, then he or she cannot see the assembly. Find the minimum number of students that need to be removed such that the maximum possible students are able to see the assembly. So how would we go about it? Also, let's see the constraints. So the constraint is n, that is the length of the array, or the length of the array h is up to 10 to the power 5. Individual elements, that is the height of the students, is 10 to the power 5. Also, the expected time complexity for it is order of n log n, and the expected space complexity is, or expected auxiliary space complexity is, order of n. So with that in mind, let's get started. So let's start with a very trivial solution. So what would be the finest trivial solution we can think of, or the maybe the brute force approach? So over here we were having n elements, and we had to tell that what are the minimum number of students we would have pushed out of the queue so that the rest of the students are able to see the assembly. Or in other words, we just have to give n minus the number of students that are able to view the assembly. Able to view. For example, let's take a example they have already provided. So over here they had given example of h is equal to 912315. So that becomes 912315. So over here you can say that if we remove the 9th element or the 0th element, so the 0th element is 9, and if we remove the first element or the 4th indexed element, so then the remaining students, that are 1 2 3 5, can easily see the assembly, because the length of every student that is present in front of it is smaller than it. For example, in front of 2 1 is present, in front of 3 2 and 1 are present, and in front of 5 3 2 and 1 are present, and they all follow the constraint that's required. So how would we calculate this? So now, since a brute force approach would be to select all the possible possibilities, so total number of possibilities would be to either keep a particular student in the queue or to remove it. So total number of possibilities would become 2 to the power n, where n is the number of students. So this is a pretty big number. For n less than equal to 10 to the power 5 as given in the question, this would become 2 to the power 10 to the power 5, which is a very big number and definitely going to give a TLE. The space time complexity they had expected us to give was order of n log n, which is nowhere close to it. So let's think of another approach. If you think about it, then what we are finally doing is that we are calculating a longest increasing subsequence, a strictly longest increasing subsequence. So the numbers that are present at the end needs to be in an increasing fashion, right? So like the second number is greater than the first number, the third number is greater than the second number, so on and so forth. So we call it a longest increasing subsequence, also known as LIS. This is a well-known, well-researched DP problem. So let's say what's the solution for this. So interestingly enough, this DP problem also has two solutions for it. One is one can be done in the time complexity of order of n square. The other can be done in time complexity of order of n log n. But in order to understand the order of n log n solution, it would be better if we first understand the n square solution. So let's get started with the order of n square solution first. So with the example we had, was 912315. So what I'll do is that standing at a particular element, I'll look to the left of it. Do I have an element at the left which is smaller in height than me? So for 9, No, I don't have any element that's smaller than me. For 1, do I have any elements that's smaller than me to my left? No, it doesn't. It doesn't also have a smaller element to the left. Does 2 have a smaller element to the left? Yes, it does have 1. Now 1 is smaller than 2 and it's also present at its left. So yes, it's present. Also, let's denote a DP. So DP element for now would only be having ones for everything. So the reason it's having 1 is that even if a single element is present in the final solution, the answer would still be 1, right? Because even a single element would correspond to a sequence having length 1. So hence the minimum answer is 1. We are populating the DP with values 1. So over here DP not, that is for 9 is 1, DP1 is 1, 2 is 1, 3 is 1, 4 is also 1. Okay, the indexes are 0, 1, 2, 3, 4 and 5, so 5 is also 1. Now what we'll say is, does 2 have an element to the left of it that's smaller than this? Yes, it has 1. So what we can do is that we can say that dp of 2, since this condition satisfied, so dp of 2 would now be maximum of dp2 and the element that was smaller than that, 1 plus the element that was smaller than that, so dp1. So it will say dp2 is maximum of 1 comma 1 plus 1. So it will say dp2 is now 2. So now let's populate dp2 as 2. Now it will go to the third element. It will say, do I have elements that are smaller than me and are present on my left? So 3 would say yes, I do have 2. So now dp3 would similarly be maximum of dp3 or dp2 1 plus dp2 1 plus dp2. So dp3 would become 1 plus 2 because dp2 is already 2, so it would become 3. Also dp3 would check the same condition for 1 as well. So dp3 would say dp3 is max of dp3 comma 1 plus dp1. However, we have already assigned 3 value to dp3, so it would say maximum of 3 comma 1 plus 1. So 3 is max, so it will keep its original value as 3. So now value of dp3 is also is 3. We'll again go forward. We'll check for 1. Do I have any elements that are lesser than 1 to its left? No, it doesn't. So we can't do anything about it. Then we'll go to 5. Now we'll check, do I have any elements to my left that have a value less than 5? Yes, we have 3, we have 2, we have 1. So we are going to check the similar thing for all of these elements. So we are going to say dp5 is maximum of dp5 or the element or 1 plus whatever element is less than the dp of that. So over here we'll be checking for dp of 3, 2 and 1. So the index is 3, 2 and 1. So we'll be checking these values for dp3, we'll be checking it for dp2 and for dp1. Now we know that the values for dp1 is basically 1, so it will become 1 plus 1. The value for dp2 is 1 plus 2. The value for dp3 is 3, so it will become 1 plus 3. So now when we'll check this value, so dp6 would become maximum of dp5 would become maximum of its initial value was given as 1, so 1 or a 4 or a 3 or a 2. So it will attain the maximum value. The maximum value over here would be 4. So we can change the values over here as well. So dp of 5 becomes 4 now. At the end, now we can say that we have a longest increasing subsequence of 4 digits or of 4 elements. So now when we'll have to return the elements, so we have to return the number of elements or the number of students that need to be removed now. So since 4 students can be present in the queue, hence only n minus 4, that is 6 minus 4 equal to 2 students need to be removed. Let's check if this makes sense. So yeah, you can see that for this particular example where n was 6, the number of students was 6 and this was the sequence, our answer was 2. However, this is an order of n square approach. So now let's see how to do it in order of n log n. but first let's understand that why it was order of n square approach. So what we were doing over here is that for every element, so for n elements, I was checking every element to its left, right? So for the first element, I was not having any elements to my left, so there were zero iterations for that. For the second element, I was having one element to its left, so one iteration. So for the third element, I was having two elements to its left, up to so on to n minus 1. Now, if you solve it, it would become n by 2 because you are having basically n by 2 terms. Your first term is 0, last term is n minus 1. So this becomes n square minus n by 2. That basically means it's a order of n square solution. So this won't pass. Let's talk about the order of n log n solution. So what we can do is that we can change the way we were storing the values in the DP. So let's say now dpj would mean what is the element at which, so over here let's say, let me give you an example so that the explanation is more clear. So we were having the array 912 315. So since the total number of element is 5, so LIS can definitely not be more than 5, right? So let's say dpj means at what element or at what leftmost element am I able to make a length of j. So for example, what is the leftmost element at which I am able to make a length of 1. So the leftmost element at which I am able to make a length of 1 is 9. The leftmost element at which I am able to make a length of 2, a longest increasing sequence of 2, would be 2 itself, because at this particular index I would be having 1 and 2. At what would be dp of 3 now? So dp of 3 would be at what element would I be able to make a LIS of 3. So over here this had a LIS of 2, this had a LIS of 1, this had a LIS of 3, right? So this would say that the leftmost index at which I am able to make a LIS of 3 is 3. Now we'll similarly calculate dp4. So dp4 would be at what leftmost element am I able to make a LIS or a longest increasing subsequence of length 4. So it would say that the leftmost element at which I am able to make a longest increasing subsequence of length 4 is the last element only, because at length 5, if you remember, we were able to make a longest increasing subsequence that was 1 2 3 5, and it had a length 4. And what would be dp5? So there's no way we can make a LIS of 5. So dp5, let's give it a dummy value, let's say it's infinity. That should do. So let's start with the algorithm. So what we can do is that in order to initiate the vectors or the DP array, let's say all the values that the DP array is having is infinity. So DP n plus 1. The reason I'm taking n plus 1 over here, because when we'll say DP n, so DP n would mean that at what leftmost element am I able to make a LIS of n, and in order to have DPN I need to have a minimum length of n plus 1. I hope zero indexed quality of CPP or of any language for that matter in computer science is well known, so this shouldn't be a problem. Also I can say dp not is minus infinity, just giving it a dummy value. Then you can start a loop, right? So what I can say is that I'll start from I is equal to 0 till the time I is less than n and I plus plus, a very basic loop. And in each iteration, so the value for that particular array that was h would be h of I. So we'll have this particular value. Now we need to check. So we also have a DP array with us. Now one of the qualities with the DP array is that if I'm having, let's say, DP3, then I'll definitely be having DP2, right? Because if I'm having a LIS of length 3, I'll definitely be having a LIS of length 2. So if dpi exists, dpi minus x would definitely exist. So if dpi exists, all the left elements to dpi are definitely gonna exist. One more thing is that the dp array would be populated in such a manner that every element, so let's say this is dp naught, that would be less than dp1, that would be less than dp2, so on to so forth. This is pretty trivial. But still, if you are not able to get it, that why this particular thing is happening, let me know in the comment section. I'll try to resolve the doubts. So with that in mind, let's get started with this particular iteration. So what we can say is that since the value we are looking for is h of I, now we need to find that am I having any lower values or any upper values than h of I in my existing dp array. Since this dp array is already sorted, then we don't need to traverse the entire dp array again. We can simply use a function known as upper bound. So upper bound is a function which is defined in CPP-STL, and we have corresponding functions in Java and Python and all other languages as well. So what it does is that it returns us the smallest value, that is greater than x. So if we are calculating upper bound x, so it will return me the smallest value that is greater than x. Just to make it clear, let's say I was having a set of 1 4 7 8 and I searched upper bound 5, so it would return me 7, because in 1478 the smallest value that is greater than 5 is 7. However, if I searched for upper bound 7, then it would have returned me 8 and not 7, because we are only finding for the greater values than the current value that has been mentioned. So I think upper bound is easy to understand, and now we have verified what upper bound, or we have learned what upper bound is. Let's go further, let's move further. So let me clear this up. Okay, so let me say that I'm trying to find some length, right? So what's the length? What I'm basically looking for is the upper bound element in my dp array which has this element I, right? So I'm trying to check what's the smallest bigger value than h of I that's present in my dp array. So it's gonna give me some values. If I subtract that particular iterator, so what would happen is that, for example, when we were talking of this particular array, we were having 1 4 7 and 8, and if I said give me upper bound 5, so it technically returns me an iterator. So iterator is basically a pointer to this particular thing, so it would have returned me iterator to this. Now if I want to get its index, what I can simply say is that give me the distance of the starting of the array and this particular point. So there's also a function called distance. So I can say give me this distance between the starting of the array, or the dp.begin, and this particular point, and this distance would technically be the index of it. So what I can say is the length is equal to dp.upperBound, the particular value. So over here as well, what we have done is we have used the similar code. So just wanted to like make you go through the code once, so that you're not lost. So over here also we are taking the distance. So as I explained, distance is a function which are given two inputs. So the first input is dp.begin, so it's the starting of the dp array, and then we are providing it with the upper bound function. So we are saying that give me the upper bound for h of I. So it will technically be returning me the length, right? Now what I can say check is, so once I have the length for it, what I'll be having is this particular value. So the dp of length would in turn basically mean 7 only. So dp of length in our case would be 7. So what I can check, is that if 7 is greater than the current element I am having, and the number that is just before 7, so the number just before 7 is 4, right? And is 4 greater than I? Basically 4 is greater than I, and 7 and I is less than 7. Only in that case it would make sense to replace 7 with the current I, because if I already was having a low value at that particular location, okay, so if I'm already having a lower value at that particular location, there's no point in replacing that. So I can have a if the value of dp length is less than is greater than the current hi, and the dp of length minus 1 or the previous element is less than h of I, only then it would make sense to replace h of to replace okay, sorry, only then it would make sense to replace h of I or dp of length with h of I. I hope this made sense to you. So if I already was having a bigger value at a smaller value at dp length, then there was no point in replacing it with h of I. The only sense it would make is if I'm having a, a, a larger value at dp length, then I can replace it with a smaller value. So this is a greedy approach, and we are following this. So this completes our loop. We'll loop it through 0 to n. Now let's talk of the complexity. So the complexity would be that we are doing this loop for n elements. However, in our loop we are just running a upper bound operation. The upper bound operation itself is order of n operation, order of log n operation, sorry. So in total the time complexity becomes order of n into log n, which suits. So let's look at the code itself. So in the code we are doing the exact same thing. We are firstly taking a dp array and we are initializing it with the maximum value of, let's say, int max. We are also initializing the first value with int min. So this is just a dummy value so as to maintain the constraint that the array is in a increasing fashion. So with that we are looping through all the n elements. So we are making this loop go through I is equal to 0 to n. Then we are calculating j. So j is basically the length, you can say. Now one thing interesting about this is that although we are calculating length, but length would directly mean index over here, as the starting point for this particular length was the beginning of that array. So length would in turn definitely mean index itself. Then we are we are checking for the upper bound of h of I in the entire dp.begin and dp.end. Post that we are checking that if h of I, that is if the current student has a height greater than dp of j minus 1 and it has a height that is less than dp of j, only then it would make sense to replace dp of j with h of I, right? Let's say the current student had a height of 10 and dpj was already 9. In that case it wouldn't make any sense to replace it, right? Because I'm already having a lower value, why would I try to replace it by a upper value, right? Because although if even if I had replaced it, so dp of j, or let's say j over here is 7, so the lis having 7 elements would still be having 7 elements itself, but now the end element or the end student that is present in a particular lis would be having a greater height. So this definitely doesn't make sense, because we want that in a lis of length x, the last student should be of minimum height, as minimum height as possible, right? Only then it would be easier for us to add more students. With that in mind, let's continue. So that completes our loop. Now how do we get the answer? So that's pretty simple. We can say that since we had populated it with the dummy values of int max, so we are definitely not going to check for int max. Other than that, we can say if the value is not int max, that means we had populated it with some other value. So if I am having some value at say dp6, that means, and this value could be anything, I'm not even concerned about the value, but it shouldn't be int max, because int max would denote that this operation never occurred and it's still having the dummy value. So if that particular value is not int max, then we can say that we can have a LIS of length x. Over here x was 6, so we can say that we can have a LIS, or a longest increasing subsequence, of length 6. So that's exactly what I'm doing over here. I'm running the loop for I is equal to 1 till n. Here I actually means the length of the sub LIS, and then I'm storing it in my result variable. So now I know what the length of my LIS is. However, what I need to return is the number of students that I need to kick out of that particular queue, and that would be n minus res. Now this is pretty simple, because if I want if I'm having a queue of total n student, and x students are the ones that are going to remain in the queue at the last, then the number of students I would have kicked off is n minus x. With that, we return n minus res, and let's try submitting it. It has a total of 145 test cases, and all of them pass with a time taken of 0.27 seconds. Cool. This question required some effort, because it requires understanding of DP. I hope I was able to make this concept a bit easy. Moreover, the first DP we discussed, that is the DP right over here, wherein we discussed we are going to the left and all that stuff right over here. Yeah, so this is somewhat easy. However, the DP we discussed later on, in which we got a time complexity of order of n log n, that's also that's a bit complicated, I'll say, but I hope you really got the idea. In case you didn't you weren't able to understand the concept, definitely let me know. I'll try to make a clarification video on it, and I'll discuss this particular DP approach in quite a detail. Thanks a lot, guys. Let me know if you have any questions or any problems that you want me to solve. Thanks a lot. Bye bye.